So this is a lecture about GPGPU computing applications for graphics and game development. So this is using the GPU with either OpenCL or CUDA with what it's actually meant to be for, which is graphics and game applications. This is an outline of what I'm going to talk about, the motivation for why you even want to do that, and then I'll go into a little bit of introduction to the graphics pipeline and shaders just so you understand how they interop. I won't really go into the same detail with OpenCL and CUDA because you guys know that. This lecture focuses on OpenCL for the graphics API, and then, or OpenGL for the graphics API, sorry, and then OpenGL for OpenGL graphics, OpenCL, GPGPU. And then after we introduce how to interop with that, I'll go into basic uses and paradigms for using GPGPU with game development. And some of the major topics under that is for collision detection, physics engines, AI. Then we'll talk about some of the shortcomings or why it kind of sucks according to some people, and then the future of interop, which is why it's getting better moving forward. So motivation. Obviously the GPU architecture is highly parallelizable. You can get significantly more floating point operations per second out of a GPU than you can a CPU when it's utilized correctly. There's programmable GPUs are now ubiquitous, and obviously in the realm of game development, they're on basically everything that has graphics now. So that's desktops, cell phones, game consoles, they all have programmable pipelines which allow general purpose code to run on the GPU. Another interesting thing that I saw, actually, I didn't realize this, was so the memory wall that you guys know all about for processor versus RAM speeds, where RAM speeds are not increasing anywhere near the same rate as processor speeds. So actually GPU RAM speeds are increasing quite a bit more quickly. Their bandwidth's increasing quite a bit more quickly than CPU RAM, so that's another reason, is that the memory wall on a GPU is not as pronounced. GPU speeds are also increasing at a much higher rate than CPU speeds. By some estimates, it's Moore's law cubed, actually, due to the streaming nature of GPUs. So I'm just going to briefly touch over this. This is the GPU graphics pipeline. This is where you're submitting geometry in OpenGL or something, whether it's like a 3D model. Basically, it's like a 3D model. And then these are basically, oh my gosh, didn't know that happened. So these blocks are basically fixed function hardware operations. They're done by the GPU and hardware. This is memory, texture memory, frame buffer. Now these two are programmable. This is actually where your compute cores are in OpenCL and CUDA. So in graphics processing, this is your Vertex processors and your fragment processors. This is where you're running shader routines. So basically you're able to customize pieces within this fixed graphics pipeline with shaders. And that's where your general purpose kernels are executed also, is on those shader processors in the graphics pipeline. So, talk a little bit about shaders. Those are the programmable portions of the graphics pipeline. They're analogous to GPGPU kernels. A shader is basically like it's a subprogram instantiated per thread, massively parallelized over a compute unit. They're also data level parallel. There's hundreds of threads operating simultaneously. Basically, there's two kinds of shaders. Well, generally two kinds of shaders: vertex shaders and fragment shaders. Vertex shaders basically operate per vertex of geometry. So if I were to submit a quad or a rectangle, the vertex shader would be invoked for the 4 vertices of that quadrilateral. And then the fragment shader would be invoked for every pixel region that's filled within the geometry. So this is just a quick example shader, just so you can kind of see it. You don't really have to understand it or anything. It's just showing this is basically your kernel right here. It's a tiny little subprogram that's run So like I said, this program is run for every vertex that's submitted for like a rectangle or something. And all it's doing is it's calculating the direction of light for that vertex. It's calculating the normal, a diffuse color, and the position of the vertices in parallel. And that's all you need to know about GLSL shaders. You're an expert. So this is basically how OpenCL and OpenGL interop. Like I said, that's going to be the focus of this lecture. OpenGL has something called Vertex Buffer Objects, or VBO. Like I said, when you try to draw geometry, what you're doing is you're submitting vertices to the graphics processor unit, which is then interpolating over them and filling the geometry. Well, a VBO is basically a way to encapsulate those vertices and that data and store it on the GPU, so that every frame you're not having to submit this data from the CPU to the GPU. So it eliminates a lot of overhead, especially for complicated models. It basically lives on the GPU, which is kind of like something else we know, which is the CLMEM, which is the host side memory handle to basically a chunk of memory on the GPU. So what you're able to do with OpenCL and OpenGL is basically you're able to, when you create your OpenCL context, you're able to create it as a subset of the shared group object of the OpenGL context, which is basically saying that you're using the same address space, and you're able to map these VBOs into OpenCL generic memory buffers, and you're able to interact between the two. And that's more or less the gist of how interoping happens between the two. So the basic approach is you initialize the CL context from the shared object group, like I said, and that's basically giving OpenCL access to OpenGL's memory space. You create the objects in OpenGL as usual, so if I wanted to mess with like a texture or a 3D model or something, I would create that in OpenGL as a vertex buffer object or as a texture. And then through CLMEM or also the OpenCL image sampler, whatever data type, I forgot exactly what it was, you reference the OpenGL object. And then once you do that, you're able to use it between the two, but then you have to be careful to synchronize between OpenCL and OpenGL, make sure that one's not reading while the other one's writing, make sure that if OpenGL is going to be rendering OpenCL's output, that OpenCL is done executing before the OpenGL shaders execute. That's part of synchronization. And then when you're done, you release the CL reference and then destroy the GL object, which is basically standard. Some examples, like I said, you map a GL texture or render buffer to a CL image, so then you can do the OpenCL image processing, convolution, whatever, with the general purpose OpenCL kernels, but then you can access that texture and render it to like a game or geometry or something in OpenGL. And then two is you can map the vertex buffer object, which is, like I said, basically defining the geometry for a 3D model to CLMEM, so you can dynamically calculate colors, modify the size, position, basically dynamically modify the VBO at runtime through the OpenCL kernels. And then these are the two basic functions for how you do that. Some things to consider. Obviously, you could create them both in two different contexts and then just do something with OpenCL, copy it over to OpenGL. Obviously, it's also a really bad idea. So most of the interop that you'll see uses shared buffers because that's drastically reducing on the overhead transferring between device and host. Not to mention the other way, you'd have to transfer from device, from CL back to the host for GL. You also have to be careful with synchronization. That's handled by the host, which is basically what you guys have already seen, the CL command queue. You can block on an event or wait for the queue to finish. And then the OpenGL equivalent is GL flush, which basically tells your driver to ensure that all OpenGL rendering commands and things have been flushed and been sent to the GPU. Some more considerations, especially for game development or anything real-time, is to keep as much logic as possible on the GPU, because the largest slowdown and overhead from the whole GPGPU thing is the transfer time from the CPU to the GPU. So you try to calculate as much stuff as you can once you've transferred from the host to the device, so you maximize your throughput. And the best way to do this is in a pipeline manner, doing different operations on independent data sets. So now we're going to talk a little bit about some game development applications now that we see how these interop together. Something I already mentioned is texture processing. So you can basically pre or post process OpenGL texture surfaces completely independent of the graphics pipeline. You could also do it with OpenGL easily, but maybe your convolution kernel in OpenCL is better. Another really popular thing is collision detection. I'm actually trying to do broad phase for the final project in this class. Collision detection is basically split generally into broad phase and contact creation. And then particles and physics engines are also really popular for GPGPU acceleration, simulating them and interacting between particles. And then AI is something I didn't realize was actually starting to move to the GPU. It's not as advanced as collision detection and rigid body physics, but it's actually showing a lot of promise. So this is just an example of some texture post-processing. So you render your entire game or whatever, your frame in OpenGL to the frame buffer, and then you've bound your frame buffer to an OpenCL memory context, and then you can do convolution. That's radial blur, actually, or any kind of post-processing effects before you render it to the viewer. And that's completely independent of the graphics pipeline. Broad phase collision detection is also pretty popular for GPGPU acceleration. Well, when I say popular, I mean it's starting to be popular in academia. These aren't necessarily used much outside of like NVIDIA and AMD. So broad phase collision detection is also called spatial partitioning. It's a subset of the n-body problem. I don't know if you guys remember that problem, but it's in all of space or whatever, every body's gravity affected upon it is also affected by every other star in the universe or whatever, and you have to be able to figure out which stars are basically irrelevant when you're calculating all the gravitational forces on one body. Well, it's the same basic thing when you're doing collision detection. You don't want to check object A against object B when they're on two different sides of the levels. So it's a way to partition the problem and create some kind of data structure that basically only holds nearby bodies adjacent. As far as the processing for this, the objects can be done independently, so you can say you can partition space or look at different objects and add them to your octree or whatever data set type you want in parallel. So that works really well. You can have a kernel executing per object. It's highly data level parallel. This is just a basic example. Binary space partitioning. You're just basically cutting space into halves every time, and then every child has two children representing the two halves within that subspace. Contact generation. This is a really good one actually on the GPU. This is also called fine collision detection. It's usually very computationally intensive, especially if you have like a real rigid body physics engine, because then you actually have to know things like point of contact and depth, normals, and there's a whole lost of linear algebra. Misspelled that. Anyway, there's a whole lot of math going on, especially if you have physics, because you need more information than just the Boolean value as to whether you're penetrating with another object or not. And each colliding pair is potentially independent, so if you have a set of potentially colliding contacts, you can check them all independently of one another, so that's also very data level parallel. You can have a kernel that handles one set of, one pair of bodies per thread. This is a very common algorithm for detecting collisions between convex polygons. This is just the two-dimensional case, but it's basically a whole bunch of linear algebra. called the separating axis theorem. This was using the rigid body, actually the fine phase contact algorithm that I developed in Dr. Wells' 790 class. It was his old GPU class for a video game we're developing. This is 258 separating axis contacts. That's what's cluttering the ground, basically little particles. And it runs pretty well, 60 FPS. Physics is another really popular GPGPU accelerated application, which collision is actually a subset of this, but physics is an entire pipeline that is highly data level parallel. The stages of it are force application, integration, collision detection, and contact resolution. Force applications is just basically where you're factoring in gravity and all that. You're accumulating all of the forces from outside bodies acting upon this body. Integration is when you're actually updating its position and its physical attributes in space. Collision detection, we've discussed that. And then contact resolution is once you've generated your contacts, what are you doing about them, separating them, transferring mass, inertia, whatever. There's some considerations for this. Like I said, it's highly data level parallel because it's applying the same operations to large groups of independent objects in a pipeline fashion. Each stage can basically be a separate set of kernels, and each pipeline can execute in the GPU using input from the previous stage, so you're not requiring any CPU or host-to-device communication intermittently there, so that that's a really good GPGPU application. It's so good actually that NVIDIA is doing it with their PhysX engine, except they're using CUDA and DirectX. I don't know if it supports OpenGL or not, but so basically their physics engine is actually, the pipeline is running on the GPU there. It's a lot of particles. AI, it turns out, is starting to move to the GPU also. These have traditionally been CPU-bound problems because there's a lot of branching and a lot of divergence going on, but there's some pretty good examples that work well on a GPU. Machine-based learning is one of them because training phases for machine-based learning basically require processing a gigantic amount of data in a data level parallel fashion. Pathfinding also works well because there's a lot of exhaustive searches for potential paths there, and then you can assign each potential path to a different kernel or a different thread on the GPU, which can do that in parallel. Then genetic algorithms is pretty obvious. You're determining the fitness value of an individual from a population, and basically every individual can execute their fitness value kernel in parallel. This is like an A-star pathfinding algorithm we used in our game before. The darker quads, or the more opaque quads, are showing where that path was traversed by the heuristics multiple times. So if it's more transparent, that location wasn't looked at as many times. It's more opaque, it's looked at a lot, so you can see there's actually a lot of backtracking over previous paths, and those paths could be handled in parallel on the GPU, in theory. So I've also read some criticisms of this stuff. I've done some of it myself, and it's pretty cool. There's definitely some issues that need to be considered when you're doing this kind of stuff. The biggest one, obviously, is when your CPU requires intermediate data from your GPU. So, like I said, the physics engine is a really good example to where you have these discrete pipeline stages that are all, the output of one is the input of another. Well, there's a lot of circumstances where you actually need the CPU, or you need to send some data back to the CPU for it to do some general purpose processing, and you might even need to send it back, and then basically your combo is broken. That's substantial slowdown just doing that. It's actually what happened with one of my final projects. Is I moved the rigid body physics pipeline onto the GPU. Every stage was on there except for the contact resolution phase. My contact resolution algorithm was not parallel. I didn't realize that. It was basically sequential. When you resolve one contact, you have to go back and look iteratively at every other contact adjacent to that and update that. So basically I did all this pipeline work on the GPU, and then I had to transfer all the contacts back to the CPU to resolve them, so it kind of sucked. Branch-intensive game logic also sucks on a GPU because that you're reducing performance because of warp divergence. That doesn't really lend itself well to SIMD processing. It's also inefficient for small sets of data because, like I said, there's transfer overhead associated with this. And this whole interop between OpenCL and OpenGL is still relatively new, so not every driver implementation supports it. Or maybe they support it, but not every one of them supports it well, or the full feature subsets. So there's a lot of stuff to look forward to in the future, actually. GPU and CPU memory unification is a trend that's happening, especially in game development. If you look at the PS4 and the X-Bone, the CPU and GPU memories, is it shared on the Xbox One? I think it is. It is on the PS4, which is substantially reducing the transaction overhead, which means something like this, that's basically the biggest problem with something like this solved right there. And that's really where the industry is going. GLSL also just introduced something called compute shaders. You have pixel and fragment shaders, which are part of the graphics pipeline. They introduced something called a compute shader, which is basically an OpenCL kernel that does whatever you want it to do. So they're starting to actually add GPGPU functionality directly into OpenGL now. And then there's a lot of GPGPU advances on the horizon. Like I was looking at OpenCL 2.0. It allows dynamic parallelism to where you can have a thread spawn other threads within it. So recursive problems can be scheduled and managed a lot more easily on the GPU without needing to transfer back to the host to reschedule it. Shared virtual memory is kind of a big deal because that's going to allow you to have pointers and complex data structures, trees and graphs that can be represented and shared between the GPU and CPU. And then pipes are pretty useful especially for the pipelining. It's basically where in hardware the output of one kernel can be optimized as the input of another kernel. So that's on the horizon too. And that's it. Here's a bunch of resources. Any questions? All right, time to go.